So what are some types of remediation technology? So I'm just going to go over like some generic ones and just kind of talk about them. If you work for a consulting company, you will have your favorites that you always use. Your consulting company may be known for one particular kind, or you might work at a more progressive one, which will take some of the newest literature that's out there and try to apply it to your site and be really kind of progressive and be known for that. You also might want to, like, as it says in here, look at, how much does it cost versus how much time does it take? Does the person need this done right away, where it's going to be only maybe 5 to 10 years, or can they go 10 to 20 years for it to be cleaned up? How fast do they need it? And so the concepts of this, so there is, the bench scale, and then there's some emerging technologies before this becomes field studies, and before there's really into it, and then we can have some large scale, and then it becomes proven technology, but it also needs to be cost effective. And so sometimes people will be like, willing to take on some prototypes to try to remediate things maybe faster, try things out. So this is it's all over the place. It depends on the type of firm you work with and where you're going with this. So originally, most places in the 1980s is what was called pump and treat. And remediate all sites. What we have to do is just pump the sites and remediate it. The problem is that it just kind of asymptotically just goes to a point where this is the cleanup standard, and with time, it just really takes a very long time. You can clean up some of the big stuff right away, but it takes a very long time with pump and treat. And the other problem with pump and treat is that the way it looks, it's just, as we mentioned in class, I think Alyssa mentioned this, that it just looks like a bunch of pipes. On the corner of First and Hillcrest here in town, there was a pump and treat facility there for a long time. And there was just a fence and a truck sitting there. And people are like, what's that? And I'm like, well, it's pump and treat. And they're like, what does that mean? And then I had to explain it to them. And they're like, oh, yeah, because it's been sitting there for 10 years. So no, we just thought it was abandoned. I'm like, no, it's doing its thing. So it takes a long time. EPA is, really realized that it was slower than necessary, that Dean apples presented a really big problem, especially if we had pure phase in there. It really does work well is when we have like an elm apple and the dissolve phase stays near the surface, and you can go in there, you can dig out the soil, you can get right at the top here, and everything is near the top, near the top of the water table, which in like our area here is 3 to 10 feet, so it's relatively easy to get to. You're not talking depths, and so Dean apples caused a whole bigger problem. And then, as we talked before, you're going to get these residual blobs that are in there that are slowly dissolving and into the groundwater. And we talked all about how they get stuck in there, and we talked about that. And so this caused a lot of the problems. And so what they can do with, like, especially with elm apples, is you can put a well that just sits right on top of the pure phase, and they'll suck up the gasoline and then put it in up to here, and they'll have a separator where it is. A lot of times this oil is actually reused, or it can be sold to someplace to be burnt off. So sometimes it's recovered and re-put back into the supply, depending on what it is. But, you have a screen and a pump, and you pump up the pure phase in there. And then you can have like a dual recovery wells, and there's a whole bunch of different ways to pick up the recovering into there. Well, as we've talked in this class a lot, when we have a Dean apple spill, it can keep going down. Your pooling might not happen until it hits an aquitard. You can have fractures that are just leaking it through. And so it becomes a really horrible mess to try to remediate, especially with pump and treat at Dean apple site. And so to do the Dean apple recovery, you have to go down as far as it is finding an impervious barrier, an aquitard into there, and usually it'll go into some sort of something. Once, if you can find it, you can find these pools, you can pump them up. The remediation technologies, we're going to really talk about some introduction to them, pump and treat, and some other technologies used. So pump and treat for dissolved apples, the key concept is a number of pore volumes, and it takes a long time in order for that clean water to finally dissolve all of them. And so what do these sites look like? These are typical what pump and treat looks like. You'll have some sort of, the well will pump it up. There'll be some sort of in situ treat or ex situ treatment, some trailer like this, and then they pump the water right back into the ground. These can be used for dissolved NAPLs into the system. NAPLs are sorry about that. There's a notification here. So NAPLs are very soluble compounds, especially soluble ones, into the areas. So some other type of technology besides pump and treat that they use is, and we're going to talk about these, is barriers, containment, natural attenuation into the systems. So one of the other things that we can talk about is the number one thing that they do to remediate a site is just digging it up. Is they haul it off to a landfill or to an incinerator, and you just dig up the contamination. Well, especially if it's a DNAPL. And so here's just some examples where they're just taking all the soil from the site, they put it into trucks, and then they drive it away. And so there are certain landfills that will accept these type of soils. There are certain places that incinerate them. And so there's certain types of places that you can send it off to, and the cost benefit, again, to your client depends on how much money they have to dig it up, to incinerate it, and then refill back in. But this is the first steps into it. Another thing you do right away is you pool all the tanks. And so tank pools happen all the time. So these are what gasoline tanks look like below the ground. Here's a gas station in there. And so you pull these tanks out and remove the source of the pollution and then the soils around it, and then you can put in a pump and treat system in there. So excavations, usually you can go down about 25 feet. You have to dewater the site, so you have to make sure that there's no water coming in, so you're having to put that in, so you may be putting in barricades around it. So these work great for small settings and small areas. Another technique that is used is called soil vapor extraction. And what you're doing here is, again, we talked about VOCs and turning things into a vapor. And so what you're doing is you have a vacuum here, and you can either be blowing air into there, so you can blow it in and then you suck it into another well, or you could be having these completely empty and putting a vacuum on top of it. And so what you're trying to do is, before it even hits the water table, as you're in the vadose zone, you're sucking in all of the material from the vadose zone into here, and then once you sucked it up into here, then you extract out the vapor in there. So if you have these things, if we increase the vapor pressure, which we talked about in this class, you're more likely to have success in it, and with a coarse grain thing. So if you looked at the vapor pressure of the different compounds you're in there, the higher the vapor pressure, the more easy it is to become a volatile compound, volatilizes and goes into a gas. Easier it is for it to remediate. Also, if you're in a sand, as soon as you get into silts and clays, it gets harder and harder to suck that air through the system. So some basic design processes. So you have to have air permeability. So you have to estimate the soil properties to see how easy it is. So you test it. You can do contaminant characterization. So, which DNAPLs do you have there? Which LNAPLs? What's their vapor pressure? Look at their Henry's law coefficient. You have mixed compounds. So that's why we went over a lot of those things. And then what type of airflow do we need? How far away is the water table? Is there pumping still needs to be done because some of it's gone down there? What's their stratigraphy like? And so that can cause problems. The other thing you could do is bioventing, which is instead of sucking air, you're injecting air into a volatile phase to cause it to degrade. So we talked about aerobic biodegradation. And so some of them just need more oxygen added to it to help break it down faster. So you can do that. So you slowly add oxygen to the unsaturated zone. This increases the biodegradation that's already naturally there. You're keeping it all nice and aerated. You're giving them more of the foods that they need, and they'll break down the compounds. So it's enough way to do the treatment. And then you can also, when I've seen this done, they've also put a soil vapor extraction in there too. So they're blowing the oxygen into the air to help it. But then if anything is getting off, they start to clean those sites off. So bioventing process overview, you're injecting air into the unsaturated zone. You're trying to stimulate that aerobic in situ, especially if the compounds are like BTEX. They break down very quickly. You've got isooctane into there. You inject is slow to minimize the release of organics. So you don't want to have it so that, you're like walk across the site and all of a sudden you're breathing in all the fumes into there. And there's no need to treat the vapors. Hopefully, once it's been biodegraded, you're mineralizing it. So you're changing it into CO2 and water. But, you sometimes depends on the site. You got to look at every site completely different. And so bioventing design approaches, so you have in situ permeability test, you can do some respiration tests to make sure that the compound will biodegrade. So when we talked about Monod's equations and we talked about first order rate kinetics, that's where this would fall into there. You can install a couple wells in order to do it, some PVC vent wells, you're spacing them out. And then injection is variable. So depending on your site, you can set these up. The next one that we're going to talk about is in situ biodegradation, which we kind of talked about with the soil venting, but oxygen release compounds. So again, this is in situ biodegradation. What you're doing is you're not just adding the oxygen, but you're also adding other types of things to it. So especially if it's into the water table instead of the vadose zone. And so what you're doing in here is you're giving the microbes that are at the site the other things that they might need. So you do a site investigation, you look at it, you're injecting in. Does it need a co-metabolite? Does it need no oxygen? Does it need oxygen? Does it need nitrogen compounds? So what you're doing is you're adding in the compounds that you are interested in to help, and then you put it into another well, and you're pumping the solution through, and you're hopefully basically doing the degradation or the breakdown in situ in the ground instead of up above. But a lot of times this won't remove everything, and so you're still doing pump and treat. So you're helping to reduce the concentrations that you have to treat above and hopefully speed up the process. So the sites with non-chlorinated compounds like BTEX, creosotes, our PAHs, our naphthalene, coal tar, sites with depressed oxygen, and aquifers with high permeability. These work great. Again, once you get into clays, you can add what are called oxygen release compounds. So this is KMNO4 or potassium peroxide. I always just like saying KMNO4. I think it's just kind of fun. Kind of reminds me of saying my ABCs. Potassium, the potassium permanganate is the other one. And then magnesium peroxide is another oxygen release compound. And what these do is they release oxygen compounds into the system. And so what they do is as they're getting water, they activate them and they start releasing compounds. They help to oxidize the compounds. These are really kind of like you can inject it and then get it into the oxygen release compounds. And then here you're blowing the volatiles into here. This is the blower. This is kind of what I was talking about before with the air sparging. And so this way you're really trying to remediate a site that has a lot of heterogeneities into the system. You can get certain circuits to air sparging. So what can happen is if you have a clay layer here, and here's your contaminated zone and all the, so you have to know your geology of your site. And so you may be blowing all this air down here, and this is your pollution. And so, especially in Illinois where, we can have these clay lenses and sand lenses everywhere. So it's really actually quite complicated. Another type of remediation are barriers. And so the purpose of this is to, if you've got your site, you don't want the groundwater to leave your site. And so you're trying to contain it into there. So the routinely only goes down to about 50 feet, but they're very expensive. And you can put in slurry walls around the outside. You can also put in treatment walls, so you can force the groundwater to go through an in situ treatment train. This is commonly used with zero valent iron. So zero valent iron will go through there and will clean up the site in there and stuff. So what can happen here is you get these low permeable barriers. So the flow, you've got your aquitard, it kind of stays where it is. And so groundwater will have to flow around it. So we get these groundwater flowing around the DNAPLs as they're stuck inside of the system so that the groundwater flow is not impacting other locations. You can also do what's called hydraulic containment, where as the pollution is moving, you're like, no, don't go that far. And so you're using pumping wells in order to contain it, to keep it from going off of site or going into, say, drinking water sites into there. And so we use modeling in order to predict where we can put in wells in order to contain the hydro. So instead of putting in walls, we can put in these wells. So one of the examples of this I like to show or go to, and we could do field trips, is go out to the BP manufacturing facilities out in Whiting, Indiana. So along their entire property, they have wells that are installed right in and they're pumping the water and the pure phase compound so that it stays on their property. Whatever they pump up, if it's got oil into it, they put it back into the manufacturing facilities in order to kind of like contain everything onto their property. And so we can go and see those. However, they don't work great. We have a well that I know of that is just over their property line, and we've played in it, and we've had like 6 feet of pure like oil, and that's off of their property line. So sometimes, depending on the facility, they don't work great. So they really should be actually going back and redoing those again. Hydraulic contaminate with slurry wells. This way you're pumping the fears out, you've got your slurry wells, you've got your pit, you're kind of keeping everything within inside of your area. You're not allowing it to escape and maybe affecting wildlife or humans or whatever else that's out there. You can put in what are called interceptor trenches, because say you have a contamination here and this is backfilled with gravel. Well, water is going to want to go to where it's easiest to flow. So the water is going to want to go to this gravel and flow that direction before it's going to flow other locations. So you put in this gravel back trench and you pump inside of it, it's going to pull everything right to it. So this interceptor trenches, especially for DNAPLs, is a great way to go. You put it in here, and then you have a treatment unit up above on the thing. And here you have your DNAPL or your NAPL plume is going over here, and you have like a interceptor ponds that are in here where you have things floating onto it because, we're hitting the water table. And so this is right at the water table and we're sucking up all the oil and gasoline. So we know which direction it's going, and we're going to intercept it based upon the direction of flow. Yeah, there's like a little dying fish in here. And so then you can put this oil, gas is coming up here. You can put these pumps, these sludge pumps right on the top. It pumps up the oil and stuff like that. And then it allows fresh groundwater to come into here, and we're pulling off that layer. Again, I know of a site, again, in Whiting, Indiana, near the BP site, where there's a whole slew of these right along the next edge of a creek, and they have some of these on the creek, but we can still see oil like right on top of the water. Yeah, it's fun to see oil, dead fish and everything else. So again, on my field trips, I take people to these locations so they could actually see these things in real life. So when you're installing remediation systems, a lot of it is just good old-fashioned hydro. You're cleaning up the site. You're putting in wells. If you ever go to a site, you see these triangles. Those are monitoring wells. Oops, sorry. And so you can install these, here's the trench with all the sand being put into it, the gravel into the area. It takes a lot of work in order to give these things. It's very expensive for remediation, especially when you're installing like these large trench areas and stuff. So the other thing you can do is natural attenuation. It's not really a new approach. It was years ago. But basically what this is saying is if we leave nature alone, it's going to clean the site up. So do we actually have to do anything? Can we just monitor to make sure it's not leaving our location? But, if we know no one's going to be impacting it, it's not getting into wildlife, it's not impacting our plants and animals, it's not impacting any humans for health. There is nothing. No one's using, it's not going to come up and cause cancer. It's just there. Why actively remediate it? Can't we just let nature take its course? It takes a lot longer, but it's so cheap because all we're doing is monitoring it to make sure the degradation is occurring and that it's not leaving our site. So this is what happens with a lot of contamination. I brought this up at the beginning of the class and said, should we clean up every site and should everything be cleaned up? And it's like, nah, no, we can just let things take nature take its course. If it's not impacting anything, is there a reason to it? We do have injection wells that we inject things down below. We still have waste. And it's very, very expensive, and the amount of money that we spend to clean up something versus how much the remediation, not really worth it. So for natural attenuation, you look at destruction or biodegradation. You have numerous field sites. You study several locations in there. And so you look to see if the plume is shrinking or at least stable, if it's not getting any larger, is it getting shorter with time? Is there, your electron acceptors like oxygen going away? Are we seeing byproducts of the degradation? And so if you took like a geomicro class or you take other of my classes, I go more into this in the activation bacteria in there. And so, BTEX compound will be here, no BTEX around it. We know there's no oxygen, there's oxygen here. And since oxygen needed for breaking down gasoline is there, we looked at, there's oxygen around it. The plume is staying stable or getting shrinking. This happened at the Bemidji site. Very easy to remediate that. So that was just a quick introduction to everything you need to know about biodegradation. Again, if you're going to be doing biodegradation at a site or remediation of a site, every company has their own way of doing it. There are newer technologies. But what I went over here is just giving you like an overview of all the major ones that everybody uses generally to clean up sites. And this is what a lot of students end up getting jobs doing.